Hello, Algebra 2. Welcome, welcome, welcome. We're on the next unit. It is characteristics of functions and relations. We're going to start with CFR. I know, not very great at naming, right? CFR1. I can determine and apply domain, range, and end behavior of functions and relations. Now, most of those words we know. Most of those words we know. So we're going to start there, okay? We're going to start with here. We're going to start with domain. Domain, if you think back a little bit, domain is your X values. So let's kind of put this in here. X values. We'll get a little more specific as we go along. Range was your Y values. This is a term that we haven't done yet. End behavior. End behavior. You can kind of get an idea of what the name is. End behavior. What happens at the ends of your functions and relations? What happens at the ends? So that's kind of just a little preview of where we're going when we go. But to start out with, what we need to start with here is intervals. We need to understand intervals, and more specifically, what a finite interval is and what an infinite interval is. And when I say that, what I'm trying to get here, an interval, just in general, an interval is just part of a number line with no breaks. So part of a number line with no breaks. Part of a number line with no breaks. Okay. Now, you haven't maybe heard of that next term, finite, but you've heard of the next one, or the third one down there, the infinite. All right. I know it sounds like it should be finite, but finite and infinite intervals. A finite interval is bounded on both ends. In other words, it has endpoints. Bounded on both ends. It's bounded on both ends, or, has endpoints. So if I was thinking about this in terms of a number line, I could have 4 different scenarios in this case. So I'm going to draw 4 different, pretend number line scenarios here. Okay. I could, let me erase these. I'll try this again. Put a little closer together. I could have this. I could have 2 closed dots. We'll talk about what those mean in a second. I could have 2 open dots at the end. I could have a closed on one end, open on the other, or I could have open on the left end and closed on the right. Now, when we're going back to this, what does the open versus closed mean? What does the open versus closed mean? I'm going to kind of do a little kind of aside here. If I've got this closed dot, we say that value is not, or I'm sorry, that value is included in our set. So in other words, the open or the closed dot includes, and the open dot does not include. Does not include. And again, you're going to see what that means as we get more into it. I just want to kind of introduce you to the language we're going to be using. Infinite interval, infinite, when you think of, to infinity and beyond, hopefully I don't get like copyright for that one. But anyway, an infinite interval on either one end or both ends is what we call unbounded. So bounded kind of, kept things together. Unbounded means either one end goes to infinity or the other end goes to infinity, or they both go to infinity. What does that look like here? So again, infinite interval is unbounded on one or both ends. Okay, let's think of all the ways that this could look like, right? I could have completely unbounded. Both ends go to infinity, all right? I could have one end go to infinity and one end not. This also could be like an open circle. I could also have infinity going this way. This is what I mean by unbounded on one or both ends. Now, I'm just talking about this in terms of a number line, but we're going to apply this to functions. Functions that move all over the place, or relations that move all over the place, okay? And to really get a good feeling, a good handle on that, we have to look at interval types, descriptions. Now, a lot of this, again, this is gonna be pretty wordy. There's not a lot of calculations in this part, which is nice, but it's a lot of the description. So if I want a finite interval, I can do 3 different types of notation, or an infinite interval. I'm just doing 3 types of notation. We've got inequality notation, which has inequalities in it. We have set notation, which is basically inequality notation with some fancy brackets or curly brackets on the outside. And we have interval notation, which has either some square brackets or some parentheses in this case. So a lot to read here. I'm going to go through this and then we're going to kind of chat about this, right? If I have this here, all real numbers from A to B, including A and B, that means it could be A, it could be B, and it could go in between. A we would call included, B we would call included, and it could go in between. Remember that thing we talked about? If you know, going in between and including, it would look something like that. From A to B, including A and B. Now, finite, it could have been open on both ends or open in one end and closed on the other. It's just a finite interval. It goes between 2 values, okay? And we do that, we've got this inequality we write it out as. And for set notation, we take that same inequality and we have the fancy bracket, this curly bracket on the outside, and we say X with this vertical line, vertical line. What does that mean? I wish we had something there that says that. Oh, hey, for set notation, that vertical bar means such that. You would literally read this part right here as X such that X is between A and B, including A and B. Okay, and interval notation, we're going to use parentheses and square brackets to determine things. I personally love interval notation. I think, in my opinion, it's the most efficient way to do things. Now, we still need to know all 3, and that's okay, but I love interval notation, okay? We've also got different sets of infinite intervals. You could have greater than a number. So basically, this is saying X is greater than A. So you start at A and everything bigger. So it's going to infinity, okay? We can represent that a few different ways. You'll notice that when we had equals to, we had the square brackets. Yeah, so it's equal, less than or equal, or less than or equal to, right? Square brackets, just in the same way, we have not equal to, we have a parenthesis. We're talking about infinity, positive and negative infinity in a second, but now we've got this or equal to on this bottom one, all numbers less than or equal to A. And then we've got A is the biggest it can be. It could also equal A, so you'll notice there's a square bracket. And I just want to take a second to ask you this question, because in a second on this Edpuzzle thing, it's going to pop up and ask you a question. What's the number for infinity? Go. And awkward pause there. Yeah, we don't know the number for infinity. That's the whole point of infinity. It's some concept that doesn't exist. It just goes on and on and on and on and on and on. On and on and on and on and on. That's where it just goes on forever. It's a weird concept to think about, but that's infinity. Okay. We don't know the number for infinity, so we can never put a square bracket on infinity. We don't know the number. There's no exact value for infinity. Never put a square bracket with a positive or a negative infinity. Okay. So some of the things that I want to make notes of here before we're going to go on, we're going to talk about all these things more. It makes more sense as we do examples. So we've got the chatter out of the way. Let's do some examples here in a second. Again, an interval notation parentheses. Parentheses are not included. And it could be just one or the other. It doesn't have to be both parentheses. And square brackets means the values are included. Again, in that last note, positive infinity or negative infinity will never have square brackets. If you could somehow find the number for infinity, one, dead, you can't. But if you somehow figured it out, let me know. We'll make a ton of money. Okay. Let's see what this actually means. All this stuff I've said, what does it actually mean? Okay, let's go here. All right. And again, these are just examples. These are just examples leading us into what we are doing. Okay, we're not quite there yet. It says, complete the table by writing the finite interval shown on each number line as an inequality using set notation and using interval notation. So the three different notations. I like to start with my inequality notation. I've just got an X number line in here. I've got an X number line in here, and I know X has to be between some values. The lowest value it could be is -3. The biggest value it could be is 2. I know that X has to be bigger than -3, right? Because that's my little alligator thing. It's got to be bigger than -3, and it's got to be less than 2, because 2 is the biggest it can be. And since they're both closed dots, they're included. I'm going to put or equal to signs on both of those because they are both included in that set. Okay, that's interval notation. Set notation is a thing of beauty after you've done interval notation. Why? Because you can take the exact thing that you just written here, put some curly brackets on the right side, and you'll find out that I am absolutely terrible at curly brackets on the right, and I have no idea why. But we're going to say because we're dealing in X, we've got X such that, that's our vertical bar, -3 is less than or equal to X, which is less than or equal to 2. That's set notation. Find the interval notation, write it, put some curly brackets, and if it's an X, put the X with the bar. If it's the Y, put the Y with the bar. We're just doing X's right now. Interval notation. Love interval notation. What's the smallest number? -3. What's the biggest number? 2. We got a comma. Can it equal? Is it a closed dot on -3? Yes, it is. Square bracket. Is it a closed dot on 2? Can it be equal to? Yes. Done. So much more efficient. So much more efficient in my mind. Okay. Let's look at one more finite interval. Okay. So here we've got the same numbers, but we got an open circle. So let's see how this looks again, right? I've got my X value because, it's somewhere in between. The lowest it could be is -3. The biggest it can be is +2. It's got to be bigger than -3 and at least less than 2, but it cannot equal -3 because it's an open circle. So it includes all the numbers all the way right up to it, but does not include it. But 2, it can be 2. So I'm going to put an underline there, an or equal to. And again, set notation, there we go. Write it out again. -3 is less than X, which is less than or equal to 2. Bad curly bracket on the right. Curly bracket with an X, such that, that's that vertical bar. Such that, okay? Interval notation, smallest number, -3. Biggest number, (2). Can it be -3? No, it cannot equal -3. So instead of a square bracket, we put a parenthesis. Can it be equal to 2? It sure can. We put that guy right there. Okay, those were finite intervals. Again, we're just looking at one dimension here, just on the X line, just on the X line. Okay, let's look to see what infinite intervals might look like. Okay, Inequality notation. Ooh, here's an interesting one. Here's an interesting one. I have 2 is my biggest number, okay? I've got X and I've got 2. Am I dealing with numbers bigger than 2 or less than 2? Less than 2. X has to be at least less than 2. And is 2 included? Does it have a closed-in dot? It sure does. So it could be less than or equal to 2. This includes, this inequality says I can have values, the biggest value I can have is 2, and it can be 2, and anything less than that going to negative infinity. So again, we can write our set notation. Fancy bracket, X such that, that's that vertical line, X is less than or equal to 2. Again, I have no idea why I'm so bad at making that right bracket. And now, once again, my favorite. We've got the lowest value. Well, since it's pointing this way, it's never going to stop. Never stopping going to the left is negative infinity. The biggest value I could have is 2. And what's that thing I told you on the first page? Infinity or negative infinity can never have a square bracket. So you always need to put a parenthesis. This indicates that it does not equal that number. We don't know what negative infinity is. 2, on the other hand, it could equal 2. And you're going to notice in here how these all work together. Less than or equal to, less than or equal to, can equal because it's a square bracket. They all work together. Okay, right here, I'm going to do this awkward pause, and you're going to do something in that puzzle. You're going to do the inequality set and interval notations on that second part. And go. I know it doesn't even pause that long. So let's go ahead and look at this. Inequality notation. I've got an X and I've got a 2. Okay. The numbers are bigger than 2, so X has to be at least greater than 2. And because that's an open circle, that's it. It's not equal to. It cannot equal 2 because it's an open circle. Set notation, go ahead, throw it in there. X such that X is greater than 2. Close enough. Oh, that's the best one I've ever done. And here we go. What's the lowest number it can be? What's the furthest number to the left? It is 2. 2 is my smallest number. What's the biggest number? The arrow does not stop. The arrow is going to positive infinity. You don't have to write the positive. You would have to write the negative if it's in there. Positive infinity and infinity mean the same thing. Now, can it equal 2? No. Can it equal infinity? No. Don't put a square bracket on infinity. There we go. Now, that's a lot, and I get that, and that's okay. What we're going to do though, is we're going to take this and apply this to a 2-dimensional graph, something that has both X and Y, something that has both domain and range. Let's see what that might look like. We're going on to the next page here. Again, this will be a 2-part kind of video here. Domain. The domain that we are talking about, it describes the allowable X values or inputs. Describes allowable X values or inputs. Okay, same thing, X values or inputs. In function notation, ooh, we've done that a bit. In function notation, we call this just X. That's what we call it in function notation. Okay. The range, if domain describes the X, range in this case describes the allowable y values. Or outputs. Again, don't forget, you can pause this anytime. I know I'm just kind of talking and writing. Pause it after I talk, all right? Pause it after I talk. Describes you, oh wow, it's a nice little incline, isn't it? Describes the allowable y values or outputs. In function notation, we call this f of x. Ooh, f of x. Okay. Okay, here we go. Now, what I want to talk about, I'm not going to get into end behavior quite yet. All right. I kind of want to put domain and range in here again. I'm going to kind of come back and kind of make some generalizations about it here in a little bit. Leave myself some space over here to do so. I'll do some different colors here in a bit. But what I want to do here is look at an example. I want to look at an example real quick. It says write the domain and range of the function of an inequality using set notation, using interval notation, and also inequality notation. Okay. So in other words, I'm looking for the x and the y values. If I look at this on 2 dimensions, I am looking to see what's my smallest x value, what's my biggest x value. So for my domain, I'm just going to kind of think about this. What's my smallest x? And what's my biggest x? Okay. And if I look at this example, this is a great example of a parabola, right? This is like x squared. Actually, it's not like, it is x squared. And if I look at this, notice how these arrows would keep going and going and going. And I'm thinking of, I'm trying to figure out my smallest x value. Is there an x value where this stops? No, because this arrow points, it keeps going this way, right? Keeps going this way. But if I kept following it this way, if I plugged in an x value, I would get a y value. If I went further and plugged in an x value, I get a y value. If I went even further, if I'm off the screen, if I plugged in an x value, you know what I would get? I get a y value. There is no stopping the smallest x. In other words, the smallest x in this case is negative infinity. Just like the biggest x, if I keep going this way, if I plug an x value in right here for this graph, I could go up there and find a y value. I could keep going all the way to positive infinity. That is my biggest x value. Now, we're about to do a little something in here. That I like a lot. Okay, in inequality notation, we kind of haven't talked about how we can get something like this, right? We haven't talked about how to get this one. So we're going to go ahead and do this right now. In inequality notation, it's kind of weird, right? It'd be like negative infinity is less than x, which is less than positive infinity, is essentially what that would look like, right? My smallest is negative infinity, my biggest is positive infinity. We call this all real numbers. I'm going to write this at the bottom, okay? Here's a little note here. If you have no limits, to domain or range, we call this all real numbers. All real numbers. And we have a symbol for this. That's this right here. This is all real numbers. There's not a real number that doesn't exist in this graph for the domain. I can plug in any real number in X and get a Y value. This could also be known as all real numbers. And that makes it a lot nicer to write this stuff out, right? For the inequality and set notation, you can use that. X such that X contains all real numbers. And then interval notation, you still need to write it out as the smallest is negative infinity, the biggest is positive infinity. You don't know what the values are. So now we put parentheses on. Now, oh, forgot a T, smallest X. Now let's think about it in terms of Y. Why? What is the smallest Y value? Smallest Y. And what is the biggest Y? Well, if you remember what I just did up here, I said, what's the smallest X? I went from left to the biggest X value, which was right. Left to right. If I look at my Y values, my smallest Y values are down. My bigger Y values are up. So I'm going to be looking down to up. So if this is Y, I have no Y values down here. The first Y value I hit is right there. The smallest Y value I have is 0, and I think it touches 0. We'll talk about the thinking here in a little bit here. I say it touches 0. And since I say it touches 0, it needs to show that it touches 0 in all of my notations. Let's say you didn't think it touches 0. That's okay. Just show me that all your notations are consistent. I'm saying it touches 0. And now I'm looking here to go to my biggest. So I've gotten my smallest at 0. I'm looking up. Well, these arrows are pointing up also. Not just right, but they're also pointing up. If I'm looking at that, I'm going, hey, wait a second. That right there means my Y values don't ever stop going up. Well, what's not stop going? What's unbounded? This is an infinity. It goes to positive infinity. My Y values will never stop going up, will never stop increasing. In other words, this is an unbounded type where X has to be greater than or equal to 0, because this means 0 is the lowest number and it includes 0, but it also includes everything greater than 0. Oh, wow, I just said X. I am so sorry. Y is greater than or equal to 0. I got a little excited, okay? And so now we need to do the set notation like that, the set of all numbers of Y such that Y is greater than or equal to 0. Interval notation, we've essentially already written this when we did our smallest and biggest. The smallest value is 0. The biggest value is positive infinity. I'm looking here. I said it touched 0. And notice how it equals 0 here on the interval notation and in the set notation because I have an equal, and in interval notation, inequality notation because I have an equal sign. I made them consistent. Now we know infinity can never be touched. So here's what we're going to do. We also need to look at end behavior. Now, I am going to make that part 2 of the video. I'm going to make end behavior and one other thing part 2 of the video. But what I want to do right now is go back up to domain and range before I end this video. I want to look at domain and range in this case, okay? I want to talk about what I see in terms of the arrows and how do I know if there's going to be positive or negative infinities. So what I'm going to say for domain, if you see these things for domain, if you see an arrow going to the left and up or left and down, if you see either of these cases, that means your smallest x value is negative infinity. Smallest x is negative infinity. If you see arrows pointing the other way, if you see arrows pointing up and to the right or down and to the right, your biggest x will be positive infinity. That's because as I'm going this way, they'll never stop growing. My x values will never be bounded, will never stop. Okay. Now we need to think about this in the same terms of y. Try to use a different color here. Let's see if this works. If you see for y, if you see down and to the left or down and to the right, let me try this again. Down and to the right, you know your smallest y is pointing down. What's all the way down? It looks a lot like negative infinity. Your smallest y would be negative infinity because your arrows are pointing down. If your arrows are pointing up, if it looks like this on the left or this on the right, your biggest y value, if I'm looking way up there, it looks like positive infinity. All right, that's a lot to think about. I know that, okay? We're gonna take a look at end behavior in the second example in the second video. I just want you to take a few minutes, take it all in. It's okay. It's okay. Take care, and we'll talk to you soon.